Hello everyone, and welcome to session 8 of the Printed Circuit Board Design Principle and Practices. And we continue our sessions around the libraries in Altium Designer. So in our session today, we will discuss how we can create a PCB Footprint library. And we'll go over the editor, how we can do it manually, and then we will look into the Footprint Wizard. We have multiple wizards we can use to create footprint, and also we will discuss the mechanical layers in PCB design, how they can be used, and how we can standardize the process by defining the mechanical layers across an organization. And then we have footprint driving guidelines. We need to go back to drafting guidelines and do a review. So now, if we recall the discussion when we talked about the footprints and land patterns, what is really the major difference between these two? Now, when it comes to PCB assembly process or PCB soldering process, in both cases, when they do manual soldering or automated soldering, they require that the pads on the printed circuit board to be larger than the leads of the component. The reason for that is providing a good solderability of the printed circuit board, because if you design the pad to be in the same size of the lead, there is no place for the solder to go around, and these pads will be prone to manufacturing problems and issues during production. That's why they differentiate between footprint and land pattern. The footprint is the physical exact size of the electronic component on the PCB layout, and the land pattern should always be slightly larger than the footprint of any component. And always you can find land pattern recommendation in the manufacturer datasheet as well as in the IPC standard. And these land patterns, whenever they are defined in the datasheet, they follow the IPC standard for land pattern. And we'll talk about this standard as well. So footprint versus land pattern. So the term land pattern and footprint are often used interchangeably in the PCB assembly industry and also in the PCB design. So a given component could have multiple different land patterns. If you call the IPC standard for density level, so it's single physical component or single footprint for the same component, but it could have 3 different patterns or land patterns. You have the high density, low density, and moderate density, and we'll talk about that at the end of this slide itself, so we can see it in here. So that's why what means by a single footprint could have multiple patterns, but it will always have a single footprint. So a footprint refers to the actual physical size of a given component. It's basically the component you see. Now let me show you a data sheet to explain what I'm talking about. So let's take a look at this component. If you recall, this land transformer we designed a library for. We did not design a library. Basically, we copied. We did a reuse of the library for this component in session number 6, I believe. So as you can see here, this is a physical component and this is the footprint. Now, if you look at that, so the footprint, for instance, here, the bin, it's only 0.3 millimeter. The width of the bin is 0.3 millimeter. This is very fine width. If you look here, there is recommended land pattern for that component to be placed. And look what is the recommended width of the bed. It's 0.76. It's almost 2.5 times the size of or the width of the actual physical bed. So this is called the footprint, and this is called the land pattern. So the land pattern always have a slightly wider or larger beds. Okay. So the land pattern can have different component pad shape. Yes, that's true. So here you can see this is the footprint, and this is the actual physical component we were talking about. And these are the bins. They have a specific shape. But when we talk about land pattern, the pads can have different shapes. For instance, you can code bin number 1 using a rectangle, and the rest of the bins or the pads you can make them oval. So it's up to you. Now, the IPC 73-51C, which is the standards I was talking about, defines land pattern naming convention. So how these land patterns should be named. When you go and copy a component, for instance, from the manufacturer part search panel, you will see a specific naming scheme for these footprints. And this came basically from the IPC standard. And when we do automatic footprint creation today using the IPC standard or IPC compliant wizard, you will see that the IPC compliant wizard will suggest a name according to the naming scheme or naming convention defined in this standard. So you can go with it, or you can change it and edit it manually. So it's up to you, but it's always good to be in compliance with the standard. So the IPC standards defines a 3 density level for land pattern, and we have discussed these several times. So if you are not aware what is the IPC is, basically the IPC is the Association Connecting Electronics Industries. So it's a trade association whose aim is to standardize the assembly and production requirements of electronic equipment and assemblies. So everything will fall into the standards in this association. So we have level A, which is the maximum or most for low density product application. So if you have board where the components are spaced apart, you have low density of the component, you can use the maximum. What maximum means in here, the maximum size of the land pattern pads. So you can make them a little bit wider than the pads. So the second one, level B, it's nominal, which it's preferred to go with all the time unless you have a high dense board, which is moderate level of component density. So if you have board with moderate level of component density, the components are a little bit close to each other, then you can go with this nominal or median level B. Level C is minimum least, which is the case where you have small PCB. You are trying to minimize the size of the PCB and encapsulate the maximum number of components you can do on very small size PCB. And in this case, you have to go with level C. Like if you are designing a fitness tracker that is portable, you need to have it as small as possible, as light as possible. So you need to have all these components adjacent to each other. And in this case, you can go with this density level. Now, you don't have to worry about all these because the IPC compliant wizard will generate all these for you, and you can pick the one you want to use on the layout. Here are a couple examples for the footprint and land pattern. So here we can see all these footprints and land patterns. We have this case, for instance. So density level A, remember, this is the maximum. So here you have SMD resistor, and you can see that the land pattern in here, this is the footprint basically. So this is the actual bed, and this is the yellow one is the land pattern. So it's wider, slightly wider and bigger than the bed to provide a good solderability and mechanical relief for the component. So here you can see density level B, which is a nominal here or moderate. You can see that the land pattern or the pads on the PCB are smaller comparing to the high density or the low density in here. Now, if you go to the high density board, which is the least in here, if you go back, it's the least, which is minimum for high density. So you can see that the land pattern or the pads are just slightly larger than the actual physical footprint of the component. And the other example you can see here, we have integrated circuit. and this integrated circuit has 7 pins on each side. It's 14 pin. So density level A, you can see these pads are wider or bigger than the footprint leads. If you go to the density level B, they are a little bit bigger, but if you go to density level C, they are just slightly bigger to provide the enough solderability of the PCB. And as mentioned, these can have a different bad shape. And if you go back, here they can have different bad shapes, as we see in here. And this is an example for you. So here you can see you have rectangle. Here you have oblong, D shape. It goes like that, and then you have a D and go up again. It's like rectangle with a corner or a D shape in here. And here are another examples as well. So this is just a review for when we talk about land pattern and IPC standards later on during this session. So bad shapes, when it comes to bad shapes, now most component manufacturer recommended the rectangle bad shape. This is this one, which is the standard. However, when it comes to RF design, this is not good for RF design and doesn't provide good characteristic when it comes to RF design. You should avoid rectangle pads when you design RF circuitry. Now, the other type is the oblong pad, which is recommended by the IPC-SM-782 and IPC7351B. So that standard we were talking about in here, IPC7351C, is basically the latest version of the IPC7351B. So, and also in the C, the oblong pad is, it's in the C, this one is recommended. So it's only in the B. Now, when they came to the C, the new revision of the standard, they recommended the rounded rectangle pad shape like that. And they defined the requirement for this pad such that the corner radius should be 25% of the land width. So this is the land width, and this is the length of the land, and this radius should be defined as 25% of the land width. And the minimum you can go with that radius is 10 mil, which equal to 0.25 millimeter. So these are the scenarios you will see or you can do when you design a land pattern on a footprint. Just keep it in mind. This is just a quick review. So when it comes to SMD lead styles, there is a lot of different lead styles for SMD, but these are the most widely used styles, as you can see in here. And that when it comes to the land pattern will follow the lead style defined in the data sheet. So you need always to go back to the data sheet and look about the recommendation for a land pattern for a specific lead style. So the lead style is what is on the footprint, and the land pattern will follow that lead style all the time. So you will see all of these. Now, the mostly will be doing maybe the outward L, gullwing, and convex side. We'll use that. Also, sometimes we might use inward L, and maybe if you do BGA, maybe you can use this one, which is the ball grid array. It's called BGA, the shortcut for that. Now let's get started. First, we'll try to practice footprint design manually. So we are going to create the footprint manually. So here we have some like guidance when you create footprint you can follow. I put them here in the slide as a reference for you. And I picked up for the manual creation, first we need to create a through-hole footprint like this one. This is basically a 2-axis joystick with a center switch. As you can see here, all these pins are through holes. We have mechanical holes, and also we have electrical holes, if you will. So first, set the editor grid according to the footprint pitch. So this is important point, and this will simplify creating a footprint for you. And we will talk about this in a minute. Then you start placing the pads according to the component requirements. That's mean you need to go back to the mechanical design of the component, which is in the data sheet, and try to understand these dimensions and work out your footprint. Now, during placement, you can press the tab key to define the properties of the pad or the hole you are selecting and try to place before you place it. And this will include the designator, the size, the shape, the layer, and anything else. Now we will try to practice all that in a minute. So the designator automatically increments for subsequent pad placement. So when you pick up the first pad in your footprint, it will be automatic. The number one will automatically be assigned to this pad. When you place it, another one will be ready to place, and it will automatically have the designator number 2, and then the third one will have the designator number 3, and so on. Now the increment can be also defined in the preferences. You can change that. By default it's 1 increment by 1, but you still can change that based on, as we did that in the schematic. So you can change that in the preferences here under PCB editor defaults. You can change that. Now to measure the spacing between these paths when you do placement, you can use the measure distance tool under the report menu, or you can do it in a smarter way by alternating your grid based on the spacing between these holes, as we will do today. It make it much easier and more reliable when you create a component based on the grid. Altium Designer also provide paste special feature under the edit menu, where you can like paste a set of holes into the footprint based on specified distance or occurrences in the X and Y, like creating an array of holes. This will simplify things, especially when you create a connector, for instance. It's very handy for that kind of footprints. And we will take a look at that as well. So finally, solder mask and paste mask or solder paste mask are automatically calculated based on the pad dimension and applicable mask design rules. So Altium Designer will calculate these for you based on the IPC standard and create these as well. There are other notes. It's better to go through these notes before we start creating the footprint. So on the second slide, we can use tracks, arcs, and other primitives to define the component outline on the screen layer. We will see we have a set of tools we can use for making footprint drawing. Now you can place tracks and other primitives objects on the mechanical layer to define extra mechanical details. Basically, as we discussed earlier, the component outline is the yellow one, which is placed on the overlay layer, and this only defines the outline of the component. And if you want to place, for instance, 3D model, you need to assign a 3D model to a mechanical layer, not to the overlay layer. You cannot place it on the overlay layer. It has to go into a defined mechanical layer. If you want to place like an assembly outline, also you need to specify a mechanical layer to use it for assembly. If you want to add fabrication or mechanical information about the component, you can dedicate a mechanical layer for that. And we will talk about mechanical layer standardization also in our session today. One of the very important mechanical layer is called, or we need to add it to the footprint, is called courtyard, which defines the maximum dimension of the component. And this is very essential when you do placement. You need to make sure that when you place the component on the board, there will be no collision or interfering between these components, because sometimes the physical size of the component might exceed at specific height or level the actual outline of the component drawn on the overlay layer in yellow, as you can see in here. So we'll talk about this as well. So here multiple 3D bodies can be also placed to build up the shape. You can do that. You don't have to worry about the designator, the comment, or any parameter. They will be automatically added to the component. You can just align them or move them to reposition them. And these, of course, will be presented on the overlay layer, which is the silk screen. When we talk about the overlay, we are talking about the silk screen. So we will talk about this in a minute. Now let's switch to Altium Designer and start creating this joystick. Basically, this is a joystick. It has two potentiometer, basically two variable resistors, and it has a switch that closes when you push down the joystick knob. It's very simple, and these are used also in several applications, especially when you have like graphic LCD or something similar to that, and you want to move the cursor. You can use it in embedded systems application, and it's very easy to deal with. It's basically you need to connect the output of these two potentiometer into an analog digital converter pins, and you read the output, one for the X axis and one for the Y axis. And usually these are 10 kilo ohm resistors, variable resistors. So if you have a 3.3 volt supply to the first side and you have ground to the other side, now you can measure the voltage. Your voltage will vary between 0 and 3.3 volt based on the position of the knob. It's very simple and very easy to use as well. So let's take a look very quickly. Let's switch to Altium Designer, but first let's take a look at this joystick we are talking about. This is the joystick. It's basically electromechanical component, as you can see in here, and luckily Mouser provide ECAD model for that. Let's take a look at that before we move forward. Let's download that model and see what it looks like. Let's open it, because we can import it into Altium Designer, use it as it is after a verification to make sure that this is the right component and the spacing are correct, or we can modify it as well and make it better. So let's import that. We can import that in, because it's EPW file. Basically, we can go to the folder. We just download it. Here is the component. Okay, so it has a schematic symbol and it has a footprint as well, but it doesn't have a 3D model. It's easy to find 3D model for these stuff. And let's take a look at that. So basically, this is the footprint, and the footprint is pretty simple. You can see that. So this one in purple is the courtyard I was talking about, which defines the maximum dimension of the component. And here we have the outline. And so here these four are mechanical holes, just to fix the joystick on the board and provide mechanical stress into it. And these three are the potentiometer pads, but this is not correct footprint for this component because it's missing the center switch. I don't see the center switch in here, because if you go back in here, so we have a switch and we have pins for that switch, and we will see the data sheet in a minute. So that's why you need to be careful about using libraries downloaded online. You need to verify these libraries before you can use them. Okay, let's go back. Where is it? Okay, so this is the footprint. It's not correct. This one is not correct. We cannot use it. And this is the schematic symbol. It doesn't provide any meaningful information at all. So it's just basically the number of the bins. And you can see the discrepancy in here. So the footprint is basically shows 1, 2, 3, 4, 5, 6 bins, And here you can see 10 bins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So why do you have 10 bins while you only focus on 6? So they assign the mechanical bins as part of the footprint, which is wrong. This doesn't make any sense at all. So we are not going to use it or count on it. We are going to create this component from scratch. So let's go back to our component. One thing, let me show you the component as well in real picture. So this is basically the component with a knob added on the top of it. And this is the resistor, variable resistor I'm talking about. And these are the 3 bins. You know, the variable resistors, it's basically, it has 3 bins, and the center bin changes up and down to the maximum or minimum value of the resistor. So if this one says 10 kilo ohm resistor potentiometer, that's mean if you rotate this all the way to the right, that's mean the resistance between these 2 bins will be 0, but between these 2 bins will be 10 kilo ohm. If you have it to the center, that's mean you have 5 kilo ohm to the right and 5 kilo ohm to the left, between the center tab and the center pin and the left. And if you turn it all the way to the left, in this case you have it 0 between the center pin and the left pin, and 10 kilo ohm between the center and the right pin. It's just basic a variable resistor. So, and this is the switch. It's just mechanical switch. It's a push button switch in here. You push on it, it will close the switch. When you release it, it will open. So this is just an example, and here is another example where they put this switch on a breadboard, and here they connected the things together. So they have 10 kilo ohm resistor. 10 kilo ohm resistor has 3 pins, 1, 2, and the variable bin, which is on the x-axis, and the other one also has the 3 pins. So they connected the first pin from the first resistor with the first pin from the second resistor, and this goes into the VCC, and the second side of the resistor are connected together and they go into the ground, and then you have the variable points goes into X and Y, and this will connect with an analog digital converter on the microcontroller. Now when you move this center point all the way to the top, that's mean you are changing your voltage all the way to the VCC. When you move it to the center, now you are in the center between ground and VCC. If your VCC is 3 volt, you will see 1.5 volt in here. And this is the whole concept about it. So based on the position of the joystick or the knob, the voltage will change. So you can identify the position, the actual position of the noise. And here is an example. So if you move it in this side toward this dot in here, this is what you should read on the analog digital converter, and this will assume that you have 10-bit analog digital converter. And so you can take a look at this file, and they have a small and simple code. Basically they are just reading the analog digital converter register, and here they are reading a digital bin, and they are printing out the value of the analog digital converter and also the status of the bin, input bin. So this is just an example I want to show. Our focus is not on how we can program this and utilize it. Our focus is on the footprint. And this is a 3D model for the same thing, and it's provided on the 3D Content Central, and this is exactly the same footprint. We can same 3D model for the same component, and this will be very helpful for us when we create the footprint, because there is a trick I want to teach you today, and this will help you to create a component and verify the spacing between the holes much faster. Now let's go back to the component in here, and let's download the datasheet. Now the component we are looking for is this guy in here. So if you search for this guy, it says this guy, it has a center push button, it has a 10 kilo ohm resistor, and it's drawing number 1. So we go down, so this is basically drawing number 1. This is the component we need to design a footprint for. And here you can see the mechanical outline from the top view and from the side view as well. So what is important for us in the first place is basically the hole dimensions in here. So this is our focus in here. And let me go back, so here they don't have 3D model. So two ways to find 3D model. Either you can find the 3D model by going to the manufacturer website, and they usually provide 3D model, or you can search for it online or 3D content or other website that provide free 3D model. So let's go first to the manufacturer, or you can search for the part, and you should be able to find a direct link to the manufacturer, as we can see in here. So if we click on that, you can see the component right now in here, and you can see electrical and mechanical characteristics in here and properties, and you can see there is 3D CAD step file. So you can download this file, agreement, agree, download. It will come up. Let's unzip this. And here is the 3D model. So it's provided as a step file and a 3D PDF as well. Let's open this one. Okay. Accept. So this is the component. It's nice. So this is the potentiometer, the first one for this for basically change on the y-axis, and this is on the x-axis. And this is the switch. Basically, when you push down, this will push down, and this will close in here. So these two are connected together, and these two are connected together. So if you look down, so these are the electrical pin. I need to connect 1, 2, 3 for the first potentiometer, 1, 2, 3 for the second potentiometer, and I have the pins for the switch in here. And these pins in here, these are mechanical pins just to hold the joystick and provide mechanical support to it. You don't want to like break the pads or the board when you push or move the knob. So these are good mechanical support. You don't want to put the mechanical support on these electrical pins at all, because they will break. Now, and as you can see, there are some knobs in here on the bottom, and these also part of the body of the joystick. These are mechanical features, so we need to account for. Now let's take a look at the drawing they provided in here. So let's put these side to side and take a look at that, just to understand what's going on. It's very important to plan the component and understand the mechanical dimension of it before you start doing the footprint, especially for slightly complex component similar to this one. This is not a straightforward component. Like connectors, is very easy to put footprint for through-hole connector because the spacing is known. It's very simple. Even if the connector has 100 pin, it's easy because they are all aligned. Just copy and paste, and you can use the special paste in Altium to do an array. It's very easy, but for a component like that, it's quite complex. So we can count on that. So here you can see this is the push button in here, which is this side. We are looking at the component. If you look at the top view, this is the top view, and this is exactly what you are looking for. So if you turn it like that, so these are the four pins, 1, 2, 3, 4, and here you have this feature, is basically this feature in here, and these are just holes, 1, 2, 3, 4. You just make holes that are not plated, so there is no copper inside these holes, just the fiber. You drill through the PCB and there is no copper inside. It's called non-plated holes. The other one with copper, they are called plated holes. So here, now these are the 4 other features we can see on the bottom side, and these are also mechanical. Provide a kind of alignment for the joystick on the board, in addition to the mechanical support. So then we have this mechanical support pins, and these you need to make these as plated because you need these are metal, so you can solder these, but they are not connected anywhere. So you have plated hole, you can use it to provide a better mechanical support. This will hold the joystick in place. Now then you have these 3 pins, which are these are plated holes as well, and then you have these 3 pins which are here, plated holes, and these 4 are plated holes as well. So it's straightforward and simple. It's once you understand the component, it's easy to make a footprint for it. Now the dimensions and the spacing are given in here. Now the first step, as indicated in the presentation, is to put these holes before you put any dimension or outlines or courtyard or anything else. First thing you need to do is to add these holes, and you need to define an origin point. Based on the origin point, you can do your measurements and spacing. So the first thing is to define an origin point. And origin point is always preferred to be at the corner or at the first pin. Then you can change its place later. So the question now, where should we start? Which one should be placed first? So basically, you can start from, let's start from these features for knobs in here. And these, as you can see, prohibited wiring area. You cannot wire around these because these are just holes that are non-plated. And these are used also for mechanical support, so stay away from these. And these are spaced by 9 mm in the x-axis and 9 mm in the y-axis, so they are symmetric, easy to put, and the diameter of these, they are 2.6 mm. So when you see something like that, 5-2.6 mm, that means there are 5 holes, 2.6 millimeter, 1, 2, 3, 4, and this is number 5. Now the spacing between this one and this one is 6 millimeter. Unlike these are 9 millimeter. So we can start with these 4 and then we can place this one. Let's go back to Altium Designer and let's go back to the library, our library we created through the last 2 sessions, and maybe we can open, this is can be considered as passive component. Let's create a footprint in here. Let's open this library, and the first thing, we can go to the PCB library and we add a new component here, and this new component we can call it, let's go back in here and see what was the name of it. This is the name of the component. We can use the same name of the component just to remember what is this, and we can provide meaningful information about it. Okay, and what is the total height? This is just information, and we can go here, we can look, height 12.9 millimeter. Okay, and also, yeah, that's enough. Okay, so now we have, let's delete the other one. Now we have a component, it's ready. The first thing you need to do is to set the grid. So to do that, you go to the properties in here, and on the properties under grid manager, you double click on it, or you click on the properties in here, and then you set your grid. So let's show the fine, keep it as a dots, and let's make it lines. And if you click apply, now looks like we need to zoom in. Okay, here. So this is the fine grid, and this is the course. When you see multiplier 5x grid step, it's basically between the fine and the course. Okay, so now we need to set the steps, and here is the trick. Now this is the origin point, basically this is the origin point, and the trick is in here. So the first thing we need to create is, let's go back in here. We need to create these 4 features, which are non-plated holes. Each one of them is 2.6 millimeter. and they are spaced by 9mm in X and 9mm in Y. This is very simple because it's symmetric. Now, what we can do to simplify this thing, 9mm grid. Okay, so if you zoom out, so basically it's from here to here, it's 9mm. Now the step between each one of these dots is 9mm, and this will simplify the placement of these through-hole paths. Now you select pad, place pad in here, and you can measure that. If you go to report, measure distance from here to this point, this is 9mm. So, and this is the fine grade or coarse grade, and it's five dots because it's x5, the multiplier is 5, and this is 45mm. If you measure all the way, it's 45mm. So if you change this to be 2x, and this will not be an integer number, so let's keep it as it is. Now let's remove these. You can clear it by using Shift C to clear it. Now let's take place pad from here or from the toolbar menu, or you can go to place pad. Now when you have the pad in here placed, click on tab. Once you click in tab, it will pause, and now you can change the designator, and you can change the layer, and you can change also the shape of the hole itself. Now the hole was 2.5mm. Let's set the hole size, and this hole is non-plated. There is no copper inside this hole, and since no copper inside this hole, you don't have any diameter around this area, so you change this one also to 2.5mm. 2.5mm. So it's completely an unplated hole. And now you can basically place this hole somewhere, and then your grid now is basically 6mm. You can move 9mm, and then just one step, and the cursor, basically the step is 9mm, place the other one, and that's it. So if you switch to the 3D model now, it doesn't have 3D model in here. Okay, so view, yes, it's footprint. Should have 3D model. Okay, here's the 3D model. If you look at it, it's basically just mechanical hole, nothing else. So we have problem right now, and the problem is you should not design the holes and the bed to the size of the actual mechanical hole. You need to account for tolerances. Tolerances are very, very important when you do footprint design. So the hole here is 2.6mm, it's not 2.5. We need to correct that, but you need to account for tolerances in this case, and I would set this one to 2.8mm or even 2.9mm. So let's change these. You can select all of them in the same time, and this goes into 2.8, and also these change to 2.8, 2.8, and this is basically the size and the shape of the bed in X and Y. So you can select here if you want round, rectangular, and other rounded rectangle. As we saw, you have multiple options for that. You can experiment with different options, or you can define the tolerances in here as well if you want. If you don't want to increase that manually, you can set the tolerances to be 10% or whatever, depending on the information in the datasheet. So this has to be 2.6. Okay, now let's place the fifth hole, which is spaced by 6mm, and it's in the center, exactly in the center. Now first of all, let's change our grid to 6mm. Very easy, very simple. Copy this bed, and now Ctrl V, as you can see, it's off grid. So the easiest way is you can change the grid back to, let's say, 0.5 millimeter, because you have 9 millimeter and you need to position this at 4.5, which is the center point between these. So you can copy any of these points. Better to copy the one at the origin. And now you can, this is the center point, you can move it down, and then you do the measurement, report, measure distance, and you can click on here and go all the way to the center and look at the X. So it's 6 millimeter, X distance, Y distance, sorry, 6 millimeter, and its Y distance 4.5, which is the center point between the 9 millimeter exactly. Why this became very simple? Because I know it's 9 millimeter, I need to move 6 millimeter by 4.5 millimeter. If we go back to here, so it's exactly in the center between the 9 millimeter, which is 4.5 millimeter, and I need to move down by 6 millimeter. So change it to 0.5 millimeter, and in this case I can move it to the center. If I change it by 1 millimeter, I cannot go to the center point because the step will be 1 millimeter. So it's done. Shift C will clear these dimensions. Now I have the 5 mechanical features, and I can add the rest. Now let's add these 4 mechanical support holes, and these are plated. Let's take a look back on the 3D model. We need to add 1, 2, 3, 4. And now let's see how we can base these 4s. If you look at these 4s, you can see that they are spaced by 15.5 millimeter on the X and 13.3 millimeter on the Y axis, and they are also aligned with the center. One thing we can add now and learn to add is something called grid manager. So what we can do, we can add a guide. So we can add horizontal guide. Okay, click on it and place a horizontal guide, and we need it in the center exactly, and this is horizontal. Okay, this is, and also we need to place a vertical guide also in the center, and we don't need. Okay, so here you can add guides. These are just for your reference. When you do a design, you can remove them later, and it's easy to remove. You can just come here, select all these, and click on delete. Like, we don't need the first one, we can delete that. As we can see here, the horizontal guide is not in the center because the center should be 4.5 millimeter. So we can fix that, and this one is in the center vertically 4.5 millimeter. Now what we need to do is to position the other mechanical support holes that are plated in reference to these. So they are spaced by 15.5 millimeter on the X and 13.3 millimeter on the Y, and the diameter for these holes is 1.5 millimeter, and we have 4 of them. So we need to account for tolerances as well, and usually you can account for 5 to 10% tolerances on these holes. So let's set this one to 1.7 millimeter. So we can go here, we can select a pad, place pad, tab. Now we need to change that. So this is 1.7 millimeter, and now this one is plated. Now this 1.7 millimeter is basically the hole that shows in the green. Now if you go down, now the cover around this hole, or the diameter around this hole, is defined in here. So for 1.7 millimeter, you can define the outer diameter of the pad. So the pad basically It's a hole plus diameter, and this is the cover in here that is in white. This is basically the cover. So here 2.5, I would go always 1 millimeter cover on the top of that for mechanical support hole. So as you can see, if you add more cover for that, let's say 4 millimeter by 4 millimeter, basically all that in here is cover, and this is the hole only. So it's just 1 millimeter of cover is more than sufficient for that. And of course you can select different shape of the bed as well. So you can select rectangle, octagonal, or rounded rectangle, and you can define the corner radius in here 25% according to the standard. You can go with that, it's fine, no problem at all, but I prefer now the round one. So this is the first one. The hole is ready. We can click on, and we need to place the hole and calculate the spacing as well. Let's go back to the sheet. So the spacing between the first one and the second one is 15.5. That means from this one to the center point is 7.75 millimeter. So this is what we need to measure. We need to measure port, measure distance. We need to have, this is 7 millimeter, so we need to move it one step because each step is half millimeter. So measure again, port, measure distance. So this is 7.5. It's great. Now what we can do, we can Control C, copy this one, Control V, and move it all the way to the other side. And now port, Control M, it's 8 millimeter. We need to move it one step, and now it's in the center, as you can see. Now the spacing on the other side in here is, let's go back. If you have two screens, this will help you, will be very helpful when you create layout or create footprints, because you can look at the reference document or schematic while you are designing on the layout or footprint. It's 13.3 millimeter, and to the center it would be 6.65. So from here to the center, 6.65. So let's go back to the layout. We can copy these two, Control C, and let's put it on the center in here. So we can paste that on the center, Control V, and stay with the center. And I'm assuming it's in here. Now let's measure that. Report, measure distance. We can measure from bed to bed or bed to the center. So it's 14 millimeter. It's supposed to be 13.3. And we need to 6.65 to the center. So let's calculate, or let's measure 6.65. So if you look at here now, if I put it in here, start moving, it shows 4 millimeter, 4.5 millimeter, 5.56, and 6.5. And we need to change the grid to increase the resolution because 6.65. So our resolution is half millimeter now, and we need much finer resolution to move to 6.65. This is gonna be tricky. What is the simplest way to do it is basically to use a grid manager and place horizontal guide and vertical guide, and this will make it simpler. Now you need to understand that when you put a horizontal guide 7 millimeter and 7.5 millimeter, these are relatively to the origin point. Now we need to move this point by 6.65 from this center point. What you need to do is to move your origin point to this center point, and you can do that by going to Edit, set reference location and move your cursor to be aligned, the yellow cursor to be aligned with the green cursor. Click on it, and now your oh, it did not move. You need to change the resolution, change it to 1.1, and now we can move it, edit, align, set reference location, and still we don't have enough resolution. Okay, align. If this happens, that means your grid resolution is larger than the position of these lines. So let's set reference location as in here. Okay, let's see. Now all that we need is to place horizontal guide, and we don't care about it right now where it's positions, but let's put it in here for instance. And now we need to say this is 6.65 from this, and we need another one, place horizontal, and this has to be positive, and also it should be 6.65. Okay, just to make sure, let's calculate that. Make sure that it's, so we have 13.3 divided by 2 is 6.65. That's correct. So now all that we need to do is basically to move these holes down. You can select Control, click down, and you can move them until the center of the hole is on the reference line in here. So let's do the other two. We need to move them up. You can move them up, or you can use the snap feature. Now the dimensions here are a little bit not standard. That's make it harder. Now this is what we need so far, and this is everything is aligned now, as you can see. So we have all these mechanical holes and mechanical features. Now we need to place these bats. So these are easy to place. These are in the center because you just need to space them by 2 millimeter from these holes. And this one is on the center, and this one on the center, and this one is spaced by 3.1 millimeter. 3.1 millimeter, yes. So this is better to have a mechanical, also have another reference guide here. It make it easier. Make sure they are aligned as well. So 3 millimeter mechanical guide from these points, or you can have them, it's basically from the center. You can calculate 13.3 here divided by 2, and then add to it 3.1 millimeter. It's 9.75. It's basically from here all the way to here. It's 9.75. So let's add place horizontal guide, and we need this horizontal guide somewhere in here, and this should be 9.75. This one, 9.75. So the bats will be in here, and the first one is very easy. It has to be exactly here in this center point, and these mechanical guides make it much easier. And now we need another mechanical guide for the holes in here, and if we go back in here before we place them, we can put the mechanical guide here. So it's just 2 millimeter from the center. So the center is 15.5 divided by 2 plus the 2 millimeter, it's 9.75. It's exactly the same from the center. Okay, let's make it symmetric. So let's place now vertical guide, and we need this vertical guide somewhere in here, and it has to be 9.75. Okay, that's it. Now we can place the holes, but let's see the size of these holes. Now, as you can see, these holes are closer to these mechanical support holes, and these are a little bit farther because here you have 3.1 millimeter and here you only have 2 millimeter. So there is 1.1 millimeter difference. Now, these holes, you have 6 of them, 1, 2, 3, 4, 5, 6, and they are 1 millimeter. So you can make them 1.1 millimeter. You add 10% for tolerance on that, and the spacing between them is 2.5 millimeter. So between this one and this one is 5. That's mean 2.5 between each. So let's add that. So this is simple. So we need a hole. Click on tab, change the properties of this hole. So the hole size is 1.1 millimeter, and in this case you can make it 2.1, add 1 millimeter for cover, and this is a plated hole, and it's exactly here in the center of this point. And we have another one here in this center on the mechanical guide, and we have one to the right, one to the left, and here one to the right, one to the left with 2.1 millimeter spacing. So how we can make this easier for us? So basically, let's change the grid into 2.5 millimeter, and now maybe we cannot. Let's see. So this should be 2.5, and Control C, Control V. This should be 2.5, and here same thing, Control C and Control V, move it one step, and Control V, move it one step to the bottom, and it's done. It's very simple. Just change the grade based on your the spacing or the pitch between these pads, and it will be very easy. Now we need just to make sure that the spacing between these two covers of these holes is not smaller than 6 mil. So let's change our grid to 1 mil, and let's measure the spacing between these to have. So we have 16 mil spacing, which is more than enough. Okay, so we need just to make sure that they are not very close to each other. So what left on this footprint is just these 4 holes for the switch. So basically the spacing is 4.5 on the y-axis and 7.7 on the x-axis. So 4.5 and 7.7. Let's place them first here very quick. We need to place hole. What is the size of these holes? And these are square holes, and we have 4 of them, and it's 1.35 by 1. So you don't have to make them exactly square holes, because square holes, when you do fabrication, they are more expensive than when you do round hole, because round hole is basically just drilling. Square holes are milling process, which required more time and more tools, and sometimes it will become more expensive. Basically, you can simplify this and make them round, and you can count on this size as the maximum size. You can make it like that, 1.35, make it 1.5 by 1.5. So let's add a whole tab, and this 1.35, let's 1.5, the whole size, and then we can make it 2.3, 2.5 by 2.5. And so we need 2 of them. Let's put 1 in here and 1 in here, and now we need these to be aligned. What you can do, you can select these 2, edit, align to the top, and now they are aligned. And now let's see the spacing between the 2. We need to make sure that the spacing is 7.7 millimeter. So now measure distance, spacing, it's 9 millimeter. So what we need, basically we need 7 millimeter, and 7 millimeter, if we look at here, 7.7 millimeter. So basically this is 7.7 millimeter in here. So we need to move them, and then we can center them. So we can move it to this point, and now we can select the two, and this has to be in the center. And let's see, we can measure that. Let's see, has to be in the center. And what is the spacing? So it's 4.5 divided by 2, it's 2.25 from the center of this. So we can measure that. Tools, report, measure distance. It's from the center here to the center here. We can look at the y-axis. It should be 2.25. That's mean we need to move these by, can change the grill to 0.1 millimeter, make it easier to move them. And now we can measure that. By clicking on the G key on the keyboard, you can also have quick access to predefined settings of the grid. So I'm selecting now 0.1 millimeter. So tools, measure distance, and this here, we need Y, it's 2.27. It's we need to move it a little bit, so we need a finer grid. 1, 2, that's it. This is 2.2 millimeter. And we need to make sure the other one is also 2.2 millimeter. Measure distance is 2.2. Okay. Now we need the other two. They are okay on the top in here, and they are spaced also by 2.2 millimeter. So one thing we can do, this is how we use the reference and changing the origin point. So we can go to finer grid, edit, set reference, location, and our location is the center. Now what we can do, we can go back here and we can place horizontal. We can add it somewhere in here, and this to be 2.25. It's exactly in here. Looks like we have multiple now. Oh, let's delete this one because we don't need it anymore. Now we need to copy these two, Control C, and when you copy, you need to select now the reference where if you click on here, now when you Control V, paste them, so the hold point, the handle will be where at the point you selected. So in this case, it's better to have your origin point as the handle. Why is that? So click on Control C, don't click here or here, just click on the origin point. Now Control V and rotate these, and they are spaced with the same distance. It's much easier, and I don't even need to have this reference manager line for that, but I have it in here just to show you this trick. So again, let me remove it. Select the points or the paths you want to copy, Control C. Now the cursor will change into green, asking you to select a reference point. Look at the status bar below here. Select a reference point. Basically, this reference point is the handle when you move or paste these holes. Select your reference point to this point, because these four holes are positioned in symmetric way around this hole. So click on here. Now click on Control V and stay at this point and rotate these holes by clicking on the space, position them, and done. That's it. It's much simple and very simple. Now delete all these guides. And now let's take a look, final look. And this is the photo print, and this is what we created, and we can bring it here. Take a look at that. Okay, so it's exactly the same. We accounted for some tolerances, made these some of these holes a little bit bigger, but that's all we need. Now we need to add an outline that defines the outline of the component, and you need to look at the top view in here, as you can see in here. And this outline, you know that it's the maximum width is 20.7, and then you need to draw all that around these points. So what we can do in here, oh please, okay, can simplify it. Okay, you need to go place, and you need to select line, and now click on tab, select the layer to be the top overlay and the line width. This line width is good for me. Now we are ready to draw the line. We can change the grid, so we can have fine grid. So this will go, let's say, probably we need to make it a little bit bigger. Okay. You should not put the top overlay over these pads. It should stay away, because this is basically the silk screen layer that will be printed on the top, and you don't need the silk screen to be printed on the cover. If you send it like that to the manufacturer, they will tell you there is a problem, and also the DRC will detect a problem, and you need to correct your footprint afterward. So now you can copy this to this side, and again we can use the reference point trick. So Control C, select this reference point because you need to flip it to the other side. Control V, and now it's, as you can see, it's in here. Now click on the X key. Basically the X key will flip in the X orientation. The Y key will flip in the Y orientation. So X, Y, as you can see, click, it's done. It's quick and easy. Now we need to draw, place, also line, and we need to place the line in here. So the line is around these points. And why is that? If we look at the mechanical drawing, so basically we can see it, I think, on the 3D model. Where is it? I think I closed the 3D model. Yeah, here. So basically the outline of the component is passed by these mechanical support holes, and then we have also an outline around these. So we can place line, so it basically goes in here. And again we need to mirror this, Control C, and this is our reference point, Control V, X, it goes to the other side. It's a little bit closer, and now place line, and Control C, click on the numbers, Control V, and now on the Y, flipped, and here place line, okay, so So basically this is the outline of the component. We can make it better, of course. You need to measure these exact distances in here. Datasheet is datasheet. So you need to measure exactly so you can form it exactly to the shape of the component. Now we still need to add also the courtyard. So the courtyard goes into a mechanical layer. So let's select, for instance, mechanical layer 1. And here we can put the courtyard. Basically the courtyard goes into the maximum dimension of the board, of the component. Here it's exceed the maximum dimension of the component by at least 5 mils from each side according to the standard. This is the count yard. I know for sure that the component will not exceed this dimension, and if I want to place another component adjacent to it, I need to place it away from this courtyard. So now let's place a 3D model. Let's download the 3D model from here. I think we downloaded that, but I lost it. So let's download that again. And so select the bus, go to Altium, place 3D body, and select the model. You can view it in here. Click on 3D. You can see you need to flip it 180 degree. We can see that. So now we can place it somewhere in here and switch to the 3D mode. We can see that it's flipped 180 degree. So what we need to do is double click on it, and now you can rotate this component in here 180 degree. Let's see, and the switch, basically you hold it, here is the switch, move it, click on 0, it will be aligned, and now we need to move it to align this. Flip it upside down, it will help you to position the component easier. Now the other thing you need to do, go to the visualization and switch into orthographic, not perspective. Perspective will give you another dimension and you don't need that. So orthographic, it will look like a vertical view of the component, and you can tell now these paths are correctly positioned. And sometimes what I do some tricks. I place the 3D component first, and then I flip it upside down and start placing the paths around these holes. And here you can see these mechanical features in here. They are non-plated holes, and these are plated holes in yellow. So this is basically the component, and you can see that the overlay or the outline needs to be adjusted. We need to expand it from here and expand it from here a little bit. And this can be also solved depending on the 3D model, will help you to understand the dimensions of the component. So it's basically, this is the component. It's done and it's ready, but one thing we forgot to do is giving a unique designator for these pins. Now these pins, let's see if the datasheet provide numbering for these pins so we can follow. Yes, there is a numbering, but it's not unique, so we cannot count on it. So you need to have unique numbering, and you need to match that with the schematic. You need to be very careful. This is not good datasheet for a simple component. So basically you need to have unique designator for each one of these. You click on it, go to here, and let's give this one as number 1. This would be number 2. This would be number 3. And here we will have this as number 4 because these are for the potentiometer. And this is number 5. This is number 6. And then we have the switch. We can set as 7. And this one as 8. This is as 9. And this is as 10. And now what about the mechanical holes that are plated or non-plated? These are mechanical holes that are non-plated. Does it matter if we assign a unique designator or not, or all of them have the same designator? No, it does not, because they do not have an electrical property at all, and they are not connected to any pin on the schematic symbol. So if they all of them have one designator, let's say designator, I give them designator number 11, that's fine. This will not create any problem. And for these, they are 14. It doesn't matter. What I care about is these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These have electrical property and they are mapped into a bins on the schematic symbol. And for now, we don't have schematic symbol, but we can create one very fast. And as we learned before, so we have the symbol, we have the part number. We can go in here, and this is a schematic symbol. We can go to the manufacturer parts here. We look for the component. Basically, this is the component. Right click, import into passive schematic library as. So it will import the parameters as well as the supplier link. So this is the component we imported, and we can change the comment as we said into the designator ID or the part number. And this is Joystic. Now we can use a G for that. And here the parameters, we can hide the description. We don't need to show the description, and we can hide the supplier part number. Now the footprint, we can add the footprint because we have it. Browse. It's looks like we did not save it. We can save it. Okay, let's go back. Save it. Passive and save it. It's okay, it's in the passive library. Let's go back here, passive, add footprint, browse. Oh, it's not my library. Select the right library. It's passive, it's in here. We can see it. Okay. Okay. So we have the component now. We need to create a symbol for that. It's basically, if you go back, it's two variable resistors. Let me see here. Two variable resistors, 3 points for each, and switch with 4 points. So it's very easy to create. Basically, you can go back if you have a symbol for a resistor, and I think we have in my library, or in here. So you can go to the other symbol. This is the symbol we want. And let's go back to the passive library. This, so it's basically, and it has another pin because it has a center pin. This is can change. So well, the other symbol might be better. So base line. Let's draw a resistor. And place line. Okay, this is the center point. Now and this is the center one. We have another resistor. This is just a quick symbol X. Let's put it on the other direction because we have one for X and one for Y, so we can put them like that. And then we have also switch. So for the switch we need, can move these a little bit, and we can have place line just to make it nicer. Okay, we need switch for the center point. It has 4 pins. Okay, that's fine. The switch is exactly like that. 2 switches inside one. And now let's go back to the footprint. So for the potentiometer, we have 1, 2, 3, and 4, 5, 6. The 5 and 2 are the center. So let's go back to the schematic in here. So this should be 1, this should be 2, designator 2, and this should be 3. And the electrical type is passive. And this should be 4. And this 5. Remember, the center pins are the variable position of the resistors 2 and 5. And this should be 6. And then we have these, so 7 and 8, 1 line, 9 and 10. So this is 7, and this is 8, this is 9, and this is 10. Okay, so this is the symbol, it's ready, we can use it. So let's compile our library. This one. No errors. Now what we can do, we can go to this one, place. Here is our joystick, and as you can see, the designator and the comment automatically placed, and if you double click on it, you will see the properties, and also you will see the footprint. And now when you switch into the layout, if you add a layout and transfer, you will see the footprint, and it's ready to use. So this is the first step. We learned how to create through hole component. This is a pretty complex component. It's not easy, I understand that. So now additional designator and comment string can be included by placing the dot designator and dot comment. These are defined directives in Altium Designer. If you place these on the mechanical layer, basically when in the library, of course, basically when you go into the layout, this will pick up or replicate the component name and the comment as well. So basically these are inherently added to, they are inherited from the component designator. Let me see, where is it? Here. So from the component designator and comment in here. So how you can do that? So basically you can place string. Now select mechanical layer 1 and type this as dot nature. Now if you add this somewhere in here, for instance, now Control C. Now if you combine the library, yes, we don't need the schematic. Let me remove the schematic. Compile. Okay. Save it. Save the library. Let's create a project to show you that. File, new project, just a dummy project. Let's add the schematic sheet in here, and let's add PCB. And here on the schematic, we have this design, update. Okay, oh, we need to save it. We need to save all that. So now click on design, update, commit changes, and move the footprint. And this is the dot designator, as you can see. And this is basically the designator inherited from the component properties. And here you can change this one. If you change this one to dot comments, and I think comment, it's basically the part number. Okay, so this you can of course hide the mechanical layer in here and keep the component only, and you can see the 3D model for this component on the board. And here you can see these mechanical holes to show these features, and these are the through holes, plated through holes, and it looks nice. Everything is aligned, very well aligned. Okay, now let's continue. So okay, so creating a component using the IPC compliant footprint wizard. Now creating component in manual way is old style, and you don't have to do it all the times, because if you have an IPC compliant wizard you can do that, but sometimes we have to do it when it comes to through-hole connectors. But other than that, you can create a component in a matter of couple minutes when using the IPC compliant footprint wizards. But before we do that, so what is the difference between through-hole bed and surface mount bed? So let me show you an example here very quick. So let's go back to the 2D model and go back to our PCB library. Let's create, now these are through-hole, we can stay here. So these are through-hole beds. For SMD beds it's the same exactly, but you need to place a bed in here. Now you need to change the through-hole bed that goes into or through multi-layer. That's why you see here in the properties multi-layers, and change that into a top layer. Now I know that this will be a surface mount bed because the surface mount bed doesn't have a drill. It's just a bed, and the component will be positioned and soldered on the same side of the bed, unlike the through-hole component. Now you can change now the size of this bed in here. So usually these are rounded rectangle, and you can specify the dimension of it. There is no hole here, no properties for hole, as just the dimension for that. You can specify the dimensions for that, and you can place it. That's all. So let's set the grid to 10 mil. Let's place it on 10 mil in here, and this is the bed. This is the surface mount bed exactly. It's very simple, and all that is controlled by the properties under the layer. Through-hole beds always they have multi-layer because they go through the first layer all the way to the first layer is the top layer all the way to the bottom layer. Surface mount beds basically they are either on the top or on the bottom layer. And even for this one, this can be mirrored. Click on L, you can switch between the top and bottom. Now blue is the bottom, L red is the top. Now if you click on it, you will see it's top. If I click on the L on the keyboard, now it's on the bottom side. If I click on it, it's on the bottom side. Now you can put it in here, initially create the component either on the top or the bottom, but it's the best practices require that to create the component on the top, if you want to go to the layout, it's very easy to place it on the bottom. Just select the component and click on the bottom or click on the error command. It will flip all the way to the bottom right away. So you can create the component either on the top or the bottom side. And so let's go back to the how we can create a component using the IPC Wizard. Let's go back to the slides. So basically the IPC compliant footprint wizard creates IPC compliant component footprints rather than working directly from footprint dimensions as we did and go to the data sheet and try to figure out the land pattern and the spacing between these paths. The IPC compliant footprint wizard uses dimensional information from the component itself and then calculates suitable path and other footprint properties in accordance with the algorithms released by the IPC. And also the wizard supports 3 footprint variants. Each one has a different board depending on the board density as defined in the IPC and as discussed before. So to access that, you go to the tools, IPC compliant footprint wizard, and let's create one example. So let's go to Altium Designer and project library. Let's see my library. We created a couple schematic symbols, and some of them doesn't have a footprint. Maybe on the other library. Schematic library. Okay. Okay, we created a symbol for a microcontroller, which is good. We can try to create a footprint for this microcontroller. Now, one thing we need to do is to go to the data sheet of this microcontroller. We can go to DG key. Let's close all these. And now we can open the data sheet for this one. As you can see, first of all, this is 48-pin LQFP 7x7mm. This is the outer dimension of the chip. So if you click on the data sheet, and you can go, I think the mechanical specification are at the end. So the first one, no, it's not. There are several footprints, of course, for the same chip. You need to know the chip you are using, which is this one, 48 LQFP 7x7. So this is not the one. So this is LQFP 100. This is for the bigger microcontroller, because this is a generic data sheet for a series of microcontroller, as you can see. So the X here can be replaced by numbers. So we need, this is 64. No, we need 48. So this is the 48. This is our target. So here you can see this is 48 LQFP and 7.7mm low profile quad flat package. And here you can see the footprint and the dimensions of the footprint. And here are the dimensions. Here how you can read it. You look at, this is D, and you look at the D in here, and you can see the dimension in millimeters and in inches. And the typical is the typical value. And when you look at the minimum and maximum, this account for tolerances. This is what we were talking about. So, and here you can see the footprint, and this is basically the land pattern. So it has the same, this one is called package outline instead of footprint, and here this one is called footprint, recommended footprint. It's basically the land pattern, nothing else. And this is what you need for the design right now. So we need this sheet. Let's skip it and let's go back to Altium Designer. And in Altium Designer, we need to go to the footprint library. Let's go to passive, and you go to basically tool, IPC compliant footprint wizard. It's very simple. Now here next, you need to pick up the proper type of the component, and we are looking at TQFP. I think this is the right one. BQFP plastic quad flat pack. So you select this one, next, and here you need to define the package dimensions. So you need to take these dimensions, basically go back to the data sheet and define these dimensions. Now, first, before I forgot, this generate step model preview basically will generate much higher resolution 3D step model, and this is highly recommended to check this one, generate step model preview. Otherwise, it will be extruded 3D model that is very simple. And here you will have the high resolution 3D model, and it looks nice as well. So here, bin number 1. So we need to define these. So we need to populate all these. Let's go back. So we need to find D and E, the minimum and maximum in here. So go back to the data sheet. So we need D and E. So this is D minimum. You just copy these values now. And we need D minimum and maximum, minimum, maximum. And let's see, we need E. Same thing, it's copy, okay. And maximum, okay. And okay, maximum height A, which is the thickness of the chip. Let's see the thickness. We need A is 1.6 millimeter, 0.6. Minimum standoff height, we need the standoff. Okay, standoff. It's basically A1 in here. They call, yes, it's the same name. This is based on the IPC standard. So A1 0.01, set that. So bin 1 location side of D or E. So let's take a look at the chip. So bin number 1 is basically side of E. You see that? So this is basically D and this is E. So it should be we can see that. Okay. It's slow for a reason. Next. So lead width range. We need to provide B, the width of that. Basically, we need to copy all this information. So see if they're using the same. So B, small b, yes, it's the same symbol, which make it simpler. So let's go back. This is the B, this is the minimum, the maximum. Okay. The number of pins is 48, 48. 12. Since we have 48 pin, we have 12 on each side. Okay. We are done with B. Then we have L. L basically the lengths of the pin. Let's make sure which L is. So we have L. Okay, just to make sure it's the right one. Yes, okay. So this L, just copy and paste. Then we have the pitch, basically the spacing between the two pins. E is the pitch, it's 0.5 millimeter. 0.5 millimeter. Then body widths, we have E1 and D1. So we have E1, do we need maximum and minimum? Yes. E1 6.8, 7.2, 8, 7.2, 8, 2. Okay, it looks like now you can use the center button on the mouse, use shift to rotate, you can see it, and use the right button on the mouse to move it. Okay, we're done with that. So we have this, we have number of pins, we have 12 by 12. So let's go back to change the dot side of D. Okay, this is the right one. Okay, this is the pin in here, and it's in here. This is correct. Now let's move forward. I think we are done entering values, and so this is what we entered. Yes, next, and this is okay. Now some of the components have a thermal pad in the center. Our component in here doesn't have a thermal pad. If there is a thermal pad, you would see it. So an example, let me show you what I mean by thermal pad. So you will have usually QFP64 here. So this is the thermal pad. It's on the bottom side of the component, and usually this pad is connected to the ground. Okay, it helps with the heat dissipation of the components. Now, if we have a thermal pad, we can add it in here. And if you flip the component, of course, we need to change the size. Let's set, let's say 2 millimeter by 2, 2 by 2. And let me show you the thermal pad. It should look in here. Here is the thermal pad. You will see it. And there will be vias to connect to the ground as well. Okay. So the information we provided to the component, to the wizard, is basically only the package of the component. So the wizard build these pads automatically based on the IPC standard, so you don't have to worry about the land pattern and what is the best spacing, best size of the pad. Everything is implemented based on the standard. This is the point of this. So next, and here let the IPC wizard to calculate these values also based on the standard. Here the heel spacing is also calculated based on the standard. You don't have to worry about it, leave it as it is, and you can read the description about it. If you need more details, just click F1 while you are here, so it will take you to the document on Altium website, and you can read about this information. And let's move forward. Now here you can select the density level, so you can generate a component for low density, which is level A. And if, let me show you the difference. Now you see those pads are much longer. If you change to density B, they are shorter. If you change to density C, which is high dense port, and they are much shorter. They barely can fit they are just enough to fit these pins. And this will be calculated automatically as well, how much should be left before and after each of the pads. So let's generate it for level C next. So here also, this is the component tolerances, and also they will be automatically calculated by the wizard. Leave it as it is unless you have to change it manually for a specific reason. I never had to change anything manually. Also here the tolerances are also calculated automatically. Leave it as it is. And here you can see the footprint is 48 leads with pitches 0.5 millimeter, and use calculated footprint values. Everything is based on the calculation. Here, if you don't want to use a calculation, basically it show you the size of the suggested length pattern for every single bed based on the standard and the equations in the wizard. If you don't have to change it manually, just leave it to the wizard. So here you can select if you need it rounded or rectangle. For these, let me see if. So these are rectangle and these will be rounded now. You can see they are rounded in here. So next, here's the silk screen. Also, the silk screen for this component will automatically generate it and calculate it based on the spacing. The only option you can specify here is the line width of the silk screen. You can make it 25.25, and here you can also the dimension of the silk screen will automatically be calculated. And next, here you can select the mechanical layer. So here the courtyard will be positioned on mechanical 15, and it's also always recommended to keep it for mechanical layer 15 to place the courtyard. And this is the courtyard. Basically it's define the maximum dimension of the chip, and I will tell you why in a minute, because we have a slide on the mechanical layers assignment. And then you have the assembly information. It's recommended to have them on mechanical layer 1. And for the component body information, this is the 3D model. Basically the information about 3D model keeps them on mechanical layer 13. Why should we do that? Because in this scenario we will be in compliance with the Vault libraries and other libraries and reference design generated by Altium. This is the configuration they use. So this is very handy. Next, now if you want naming convention, also this naming convention is based on the IPC standard. If you need to assign a footprint name and you need to change that manually, you can remove this suggested value and you can change it. But this is how the standard define the naming scheme for footprints. So TSQFP, and then there is the dimension of the chip, the number of the bins, and also the density level, as you can see. And here you have a description for that. So let's leave it as it is. Next, now, do you want to add this component to the current library, or you want to create a new PCB library, or you have another existing PCB file that is not inside or open in Altium Designer and you need to port to it? Here you can produce a 3D step model if you need that, and you can make it embedded or you can generate it externally. So embedded basically will be part of the footprint. If you needed an external file, also another step file will be generated in the folder. And I don't need an external file. I need the 3D model to be embedded into the footprint. Now next, it's done, finish. Now this is your footprint. As you can see, now the yellow one is basically the overlay or the silk screen layer. Now the green one, it's this basically on layer mechanical layer 15 in here. This is the courtyard, which define the maximum dimension of the component. Now the purple one in here, if you click on tab, it will be selected. Basically this define the assembly or the placement of the component. This is for assembly, and this is the dimension of the component package. If you look at the component package, this is the dimension of it. Let me show it in 3D. So basically this is the dimension of it, and look about this 3D model. It looks very nice, it's outstanding, and it's generated in the IPC Wizard as well, so you don't have to worry about it. This is very nice 3D model. I like it. Yeah, so we have 3 mechanical layers usually in the libraries. You have on mechanical layer 13 you have the 3D model. This is the 3D model. On mechanical layer 15 you have the courtyard, and on mechanical layer 1 you have the assembly information. And you have also the pads. As you can see, they are on the top layer, these pads. And if you double click on it, you will see the dimension of the pad is 0.25 by 0.25. And what if I want to change the shape of these pads? It's easy. What you can do, go to the properties and only select pads in here. Now let's select all the pads It's very easy. You can go in here, and I need them to be rounded rectangle, and I need them to have a radius 25 according to the standard. And here we go. It's done. It's just one command you can change that. Don't forget about the filter. Once you are done, put it back into all objects, because if you have it, for instance, for the pad and you are trying to move the 3D model, it will not be selected. Only you can select pads. Okay, so this is done. All that we need now to do is to look at the designator, make sure that, so bin number 1, so this dots meaning here start bin number 1, 2, 3, 4, all the way to 12, 13, 14, all the way to 24, 25, 36, 37, all the way to 48. So you see that designators are already assigned in the IPC Wizard based on defining pin number 1. So start at side E or side D. So this is pin number 1, and it's ready. Now you can go to the schematic library, and this is the component, add footprint, and then we can find our footprint. Oh, you need to save the library first. Did we save it? Passive PCB library. Now let's add it. It's in the passive, and it's this one. Okay, and they are linked together and done. That's it. It's very simple to be done in the using the Footprint Wizard, and you can create any integrated circuit or electronic components, almost anything in the IPC Footprint Wizard. So what if I want to create this manually? So we know that the footprint for these is 0.5 millimeter, right? So one thing you can do in this case, you can go to the grid and set your grid to 0.5 millimeter, and now you can place a pad, put the pad on the right layer, and put the size of this pad is it's 1 by, let's say, I think it's 0.5. Okay, here 5. Let's say by 1.5. So let's say like that. So I know that my grid is now. I think this is very wide for 0.5 millimeter. It cannot be 0.5 millimeter, but 0.25. Sorry for that. So let's put this in here. So the spacing is basically, your grid is 0.5 millimeter, which is the pitch of the IC, and it's very easy now to play these paths. So 21, 22, 23. Every time you add a new one, it will get the designator will increment it automatically. Control V, because we did not place it. Now you are copy. The designator will not increment. In order to get the designator to increment, you need to place it as a path. So 31, 32, 33, and you can add these paths, and then you can copy them. And if you know the spacing on the other side, you can place them in the same way. And then what you need to add, the overlay layer, and also you add the other layers. You can create that manually, but Footprint Wizard will do that according to the standard, and you don't have to worry about it. Okay, so let's go back. So this is for the Footprint Wizard. As you can see, you can access that from the tool IPC compliant Footprint Wizards, and to run it, and it design footprint in accordance with the IPC standard, and provide three footprint variants, L, N, and M, which is the maximum, nominal, and minimum based on the density. But the question now, okay, the one we generated is for the high density. How we can generate another one for the low density and normal density? All that you need to do is to rerun the wizard, and the wizard still have all the information you entered. So you go all the way to the point where you select the density you want, and finish. You don't have to complete. And this is the other one. And go back tools, compliance wizard. Also go back to the point where you can change the density, and we need the medium density. Finish. And now let's save it. If you look at the PCB library, now you can see you have L, M, and N. You have all the three densities. And now when you go to the microcontroller, and I need to add the other two densities, or the other two footprints for the microcontroller, and we need M, and also I need the N here. Okay, so you have all three now. Now if we combine the library, someone might say, oh, okay, how I can select when I place this component into a schematic sheet? Basically, so when you, let's say, schematic library place, so let's say when we place it in here, let's zoom out. Okay, so when we place the component in here on the schematic, so I placed 2. So if you double click on it, you will see here are the options. You can see you have L, and you have M, and you have the N one. You can select that from here. Or if you have so many components, always you can go to the footprint manager, and if you have this component in here, you can just come to the footprint manager, say I need the M1, go to the menu and set as current, and basically now this is the one, accept, commit the changes, and basically you can see this one changed to M. And if you have so many components, you can see them in the footprint manager as well. So the IPC compliant footprint wizard can create the following footprint types, almost everything. And wizard is re-entrant, as we saw. So we generated for density L, then M, then N. So it's re-entrant. It will keep the last information you entered. And so enabling the generate step model preview, as we saw on the first dialog, provide high resolution 3D model. Now the second IPC generator in Altium Designer, which is very handy if you want to generate a huge library, it's called IPC Footprint Patch Generator. Basically, this counts on database file to read the information and the dimension of the component to generate several components at the same time. Let me show you very quick. This is handy if you want to create a huge library and you have the dimension for this component in an Excel sheet, for instance, on a database. So let's go to the library, tools, footprint library. So tools, IPC, compliant footprint patch generator. Now this is a patch generator. You have templates in here, and this will bring a pop-up of available templates. Selecting template will open the corresponding spreadsheet for editing. Now here, let's say I need again BQFP as we created for this chip. So now it will bring up the template for you. Give it a moment. It's loading up. And here is the template. Now you see these dimensions that we entered manually. Now here, footprint name, you put the footprint name. Let's say LTQFP 48. Then you have, let's say 64. Then whatever, you have a long list of components. And then you put a description for that. It's exactly the description generated at the end. If you recall that when we created this component, PCB library, this is the description that is generated. And this is the name of the footprint that we are trying to enter in here. This is the name, this is the description. And then you have these dimensions. And this is exactly what we filled in the wizard. And if you need information about this, you can read it in here. Basically, these are the legend. These are from the IPC Footprint Wizard and explain the dimension D and E, the maximum and minimum. This is just reference for you. And this is the footprint and this is the package. And you just fill in the data for component 1, 2, 3. If you have 1,000 components, you can fill that. Once you are done, you save it and close it. And the IPC Wizard will take it and generate all these components in one library for you. Everything, it's like patch generator for so many components, but you need to have this information known in an Excel sheet or database file. So this is about everything you need to know about the batch generator. I never used it, and because I don't have the information about the component in an Excel sheet, and it's easier for me to create the component rather than trying to fill the information into Excel sheet, then try to run the IPC generator, batch generator. So the next one is Footprint Wizard. This doesn't fall into the IPC standard. This has more flexibility, and everything you need to enter manually, nothing will be calculated for you. So it's you go to the Footprint Wizard in here. Okay, next. Now you select the package again. You need to select the package. So the package we are using is quad. You can select the measurement. You need a metric or millimeter. Next. Now you need, what is the dimension of the bed? You need to start creating that manually. What is the shape of the bed for the first bed and other beds? Next. Then you need to define the width of the outline, which is the silk screen layer, and then these dimensions, and you have to define all that manually. Let's move forward, finish, and this is the component. As you can see, it's very simple. It doesn't have any mechanical layers like a courtyard or assembly layer or 3D model. It's just very simple footprint. This is the old one in Altium Designer, and usually I go with the IPC one. I don't go with this one. Now, adding 3D model to the footprint in Altium Designer, it's not only restricted to the step file format. Actually, Altium Designer accepts step models like STB or STEB, also parasolid models, X_T and X_P, SolidWorks part files, also you can use them. But step is always preferred, and also you can use a combination of these. You can import multiple 3D models to construct specific shape or component. So you can download these files from the component manufacturer, or you can go into the 3D sources like 3D Content Central. This is the most famous website. It has like 100,000 of 3D components available, and you can download the files in different format. You can download in SolidWorks or in step file. If you don't have to edit the 3D model, don't download SolidWorks. Step file is preferred to use with Altium Designer, especially if you are going to embed it, the step or the 3D file model with the footprint. And also you can create, Altium Designer provide the capability to create this like simple 3D shapes. Here is an example. This is 3D model for a tactile switch, and this is created in SolidWorks. And this one also for a 3D switch created in Altium Designer, basically using basic shapes. Like you have a cylinder in here, and then you have an extruder. Here you have an extruders. You combine 1, 2, maybe 3, 4, 5, and multiple 3D extruded models to create this symbol. Because as you can see, these are the shape. You can create pretty complex shapes in Altium Designer using these symbol tools. Let me show you these tools. So here, let's say this is the package, and what I can do, I can say place, 3D body. I don't need this one. Sorry, extruded 3D body. So here let's click on tab, and here it's extruded. It can be cylindric, it can be sphere. So let's say extruded. What is the overall height? Let's say it's 1 millimeter. We don't need any standoff. Let's say it's 0.1 millimeter standoff, and let's start drawing that. So we can click on here, go all the way here, and that's it. So let's see, let's take a look. So basically we created 3D model very quickly without importing anything. Now, okay, I needed to look a little bit black. You can change the color for that. I needed to look black, and that's it. It's black right now. I need to change the height of it or the thickness of it. I need this one to be 2 millimeter. Now it's 2 millimeter. So you can create pretty good 3D models in Altium Designer. So let's say another extruded model. I need cylindric. Let's create this as it is. So let's see this one, 3, and this is 2 millimeter. You can change the height of it. This is the radius. This is the height 10. This is the radius 5. Yeah, you can create multiple objects and try to combine these to create another things like this one. So you have a cylinder and you have extruded body, and you combine both with different color, and you have switch right now. So this is this 3D model, but generally you can find the 3D model in all these in this website or other websites. It's not the only one. So this is what we talked about as well. So when create a footprint, you need to define the mechanical layers you want to use to put the 3D model, to put the courtyard, and also the assembly layer. As you can see here, this is based on the IPC 7351 standard. So the IPC defines the spacing and the nominal silk screen, the courtyard boundaries, thickness, and all different dimensions of the footprint, and these values depends on the footprint itself and the size of the footprint and the spacing or the pitch of the pads. So it's very handy to use the IPC Footprint Wizard to calculate all these values for you, rather than going to the standard or try to look at the tables to figure out what should I do, what should I use. So this is just an example for footprint created based on the IPC standard. So you see the solder mask is automatically calculated as well. Solder based automatically calculated. And here, as you can see, 50% paste mask stencil reduction on the thermal pad. As you can see, broken in two shapes to meet the standard. Now, when it comes to mechanical layer, the purpose of mechanical layer is to convey human readable information. Yet, there is no standard for mechanical layer configuration. However, as with all library components, consistency is crucial. Therefore, whatever is established for your organization should be agreed upon by all and followed thereafter. So if you create, or if your organization decided to use, let's say, mechanical layer 99 for 3D model, all the components you create, or any one of the engineers within the organization trying to create, should follow the mechanical layer standardization. If you create a component with uses a mechanical layer, for instance 60 for 3D model, and another engineer used a different mechanical layer, then there is inconsistency between these libraries. That's why there should be a procedure or internal standard when you do PCB design to define these mechanical layers. Again, there is no standard that says you should use mechanical layer 13, for instance, for 3D bodies. No, There are some best practices, and as you can see, there is some discrepancy and inconsistency even within Altium old and new libraries. They do use different mechanical layers. And here I'm showing you a good construction for and usage of the mechanical layer in here. So as you can see, this is the PCB construction. This is a basic PCB construction. For PCB, always we have a top layer, which is a cover layer. We have inner layers, and also we have bottom layers. All these are cover layers for routing traces, and of course we have insulation between these layers. We have the core and the pre-brick. Now on the top of the top layer we have the top solder, and then we have the top overlay or the silk screen, and then we have the top paste. This is the construction of the layer. Now when it comes to the design from manufacturing and the documentation perspective, always it's recommended to use mechanical layer 13 for 3D bodies. Use mechanical layer 15 for courtyards, and use mechanical layer 1 for information about the drilling, the assembly, etc. Then you can define mechanical layer 12 for assembly drawings, as you can see in here. And we will have an example to do all that. If you have mechanical layer 2, you can use it for designator, company, logo, data, signature, whatever you want to do that. And again, these are manufacturing data, and these are helpful during the fabrication and assembly. They are not related at all to the construction of the PCB or the physical PCB. These will not be printed on the PCB, and they have nothing to do with the PCB at all. Basically, when you create a 3D model for the PCB, you are helping the assembly house to do the assembly, because they have 3D perspective of that board, and also you are helping the mechanical engineer to design an enclosure, because the mechanical engineer or mechanical engineers have a perspective about the dimension of the board, etc. The assembly outlines also will help the assembly process, and so on. So there is no standard for that. If you are a solo, you can put a standard for yourself and say, from now on, for every single component I'm gonna create, this is what I'm gonna use in terms of mechanical layers. Now the question is, how many mechanical layers we can create in Altium Designer? Now starting from Altium Designer 19, there is no limit for the number of mechanical layers. Before Altium Designer 19, the number of mechanical layer I think was limited to 255. But starting from Altium Designer 19, the mechanical layer number is not limited at all. Now, let me show you some examples. So the IPC Footprint Wizard will use mechanical layer 13 for assembly outline, and I always would change mechanical layer 13 into mechanical layer, where is the assembly, which one we are using for the assembly drawings, to mechanical layer 12. Also, I keep mechanical layer 13 for the component body. Component body is basically the 3D model, which it should be. So I always prefer to separate the 3D model mechanical layer from the assembly drawing, because if you draw over on the top of each other, they will not be clear. And let me show you why. So if we go back to Altium Designer let's go back to the library. This one, for instance. Now, if I want to show the assembly layer only, so show me the outline, okay, and I need let's show this one. So this is the assembly layer. If you have multiple components, you will see only a contour where the component should be placed. Now, if you have mechanical layer 13 and 1 on the same layer, this is what you will see when you print it out. Basically, this hash is for the 3D model, and this is problematic. So the assembly layer is no longer useful. So better to separate these, not keep them on the same layer. That's why I prefer to do that. So basically the IPC wizard will combine the assembly outline and the component body in one layer. So as we did, just switch the assembly outline into mechanical layer 12. Now, if you go and take a look at Altium examples and template and try to extract libraries and component, so they usually pair mechanical layer 12 with mechanical layer 13 to get bottom assembly, and we will talk about layer pairing later on. This is very useful feature. Basically, when you flip the component from the top to the bottom, you need a different mechanical layer for that. It's much easier because when you need to print the let's say the information on the bottom layer, you need to isolate them from the information on the top layer. That's why you need two separate mechanical layers. One is from the top and one from the bottom. And also they pair mechanical layer 14 to 15 to get the courtyard. Now, again, the problem here, if you have a 3D model on these layers, this will create a problem. So you need to separate the assembly outline from the 3D bodies. And also they use mechanical layer 16 for title block. So Altium Designer templates, so they use mechanical layer 1 for board outline, and mechanical layer 3 for mechanical part details, and 4 for dimensions and other callouts. These are not related to the library. These are on the layout. So example of board outline, if you look at Texas Instrument reference design a project, they have the board outline on mechanical layer 1. If you look at Altium Vault templates, and they use mechanical layer 1 for PCB boundary, and they use mechanical layer 2 for Gerber IDs, mechanical layer 3 for printout IDs, mechanical layer 6 for Fabnos, and again these are not these are for components in addition to the layout. And they use mechanical layer 7 for the 3D body and mechanical layer 15 for the courtyard. Now these are component related and these are layout related mechanical layers. And here if you look at Altium older examples, also you have different configurations. You can take a look and keep this as a reference for you when you try to decide which mechanical layers I should use for my internal organization or my team. Now, when you create a footprint manually without the IPC Footprint Wizards, there are some guidelines you can follow. I sorted them here in this slide, a couple of slides. These will be very helpful for you. So the first thing is the silk screen outline, which is in here as you can see. So bin number 1, when you do the silk screen outline as you see in here, so this extended line that shows that pin number 1 will start in here, and or it's called polarity marking. So this will mark the polarity of this chip, or for ICs, basically the polarity marking is defining pin number 1. For capacitors, polarized capacitor defining the positive lead of the capacitors, and so on. So also assembly outline. This is the assembly outline you can see in here. Oh, sorry, the assembly outline is the brown one inside in here. This will not be printed on the printed circuit board. This basically, again, it's similar to the example in here. This will not be printed on the circuit board. This will be printed on a document file or a sheet and will be given to the assembly house to help them figure out the placement of the component during the assembly. So as you can see here, the brown one internal, this is assembly outline, define the shape of the component. If you look at this IC, it has leads in here, 6 leads in here, and this is the body of the IC. And courtyard outline, the one in purple, this one basically defines the maximum dimension of the component with some margins and guards on the side. So if you want to place another component adjacent to it, you know that the adjacent component should not get closer than what you have in here. So land pattern original marker, you see this original marker in the center in here? This basically will be the handle for the component itself, and also it shows the center of the component. And you can place this always. You can place the land pattern origin marker on the count on the courtyard outline layer, always mechanical layer 15, which we talked about. So terminal lead outline is the same thing here. Just an example. If you have a density level A, B, C, C is high density, medium density, and low density. You see the size of the bed, it's changed. The courtyard also spacing change, but the assembly outline it's the same. It doesn't change because this is the physical size of the component. And these are very nice reference comment or guidelines you can keep. So no silk screen outline under the component body, and these get covered up. So you should don't put a silk screen similar to this. This is basically assembly outline. This will not be printed as a silk screen. The silk screen is basically this and that, and if you place a component on the top, you still can see the silk screen. So if you put the silk screen underneath this component in here, even if the silk screen is not touching the pad, once you assemble the component, you no longer can see the silk screen. So there is no purpose of it. Why do you need it? So don't provide any useful purpose. Silk screen outlines visible after assembly and provide a functional use as alignment marking for PCB assembly accuracy. So they should be visible. If we look at our case in here, if you place the component in here, you still can see marking the polarity marking for pin number 1, and also you can see the outline for this chip. Silk screen outline should be inside placement counter courtyard. You cannot put these outside the courtyard. Basically, as we said, the courtyard defines the maximum dimension of the chip with some tolerances, so they cannot be outside the courtyard. These are guidelines you should follow. Silk screen outline should be mapped to the maximum component body, with one exception: the silk screen to the bad spacing rule overrides the component body mapping. Basically, let's see the next slide. Yeah, so here is an example. So this is the silk screen in the black in here, as you can see. Now the one in purple is basically the courtyard. Now these are the bats, and here you can see the origin marking point. It's in the center, and basically this silk screen is mapped to the maximum size of the body as indicated in here. But when it comes to have a bed like that, this rule will be overridden. You cannot get the silk screen outside here because the body of this cap is basically up to this point. And let me show you an example for this cap to understand what I'm talking about. Here is the cap over this one. So you see the bed is going outside the outline of the body, similar to this one. So it's outside the body, as you can see. So the outline should stop at this bed and should not go outside around this pin. Same case for this. Should stop at this and should not go outside that. Now, what if you go over the bed? This is not acceptable because again, this is a solder bed, it's a copper, and this is a silk screen layer on the top. If you go with the silk screen over the bed, basically this bed will become not solderable, and the PCB fabrication factory will return the Gerber files to you and ask you to fix them because there is a problem with that. So, and the silk screen outline should map the component body and not go around beds. This is what we talked about. So basically here it's mapping and doesn't go around the bed, as you can see in here. Also here you see it's mapping and doesn't go around the bed because this is the actual size. And look at the polarity marking in here. This is pin number 1. Polarity marking in here, pin number 1. This is according to the standard. Polarity marking in here, bin number 1, as you can see in here. So the polarity marking in here is basically this shape. Bin 1 is identified by extending the silk screen along bin 1 lengths of pad, as you saw in here. So it's extended in here and also extended in here. So reference designator struct is at least 10% of the text height. When you define the designator, which is a text, you add a designator or a text, it should be 10% of the stroke should be 10%, or the thickness or the boldness of the font should be 10% of the text height. And the 3-tier recommendation for height are, as we discussed, for if you have least density level, you need 1 millimeter. This is the minimum recommended. If you have a nominal, it's 1.2. If you have high density, you need 1.5 in terms of height for text. And here you see the IPC 73-Session recommends rectangular courtyard, as you can see in here. It's just rectangle around the component. Outline with line width 0.5 millimeter or 0.1 millimeter. The land pattern origin is typically located in the center of the gravity of the component. It's always in the center. This is according to the 7351B. Now 7351C, the latest one, recommends the courtyard. This is a typo. No, it's not a typo. It recommends contour courtyard outline with the line widths, the same line widths. So basically the contour will go over the component to show also the features of the component, where you have bats or you have corners and stuff like that. As you can see, look at the difference between this. It's just rectangle, and here you have a contour. It's basically shows the features. This is I think we ended up, this is the end of this presentation. Here you can see you have the physical component. Here you have the bats, the copper bats, and here you will see in the magenta is the courtyard boundaries. This is according to the IPC 7351 standard. And this is basically the manufacturing zone. This is just an example in a 3D model that shows the component land pattern, the package, the courtyard, and the manufacturing allowance. Now, this is just refreshing. If you remember this flowchart, create a component from scratch. You gather component information. Always, they are usually located in the datasheet. You create library project if you don't have one, or you open library project and to add a component if you already created one. You create the schematic symbol, new schematic symbol, add schematic component to the library, try to import the parametric data from the manufacturer part search. You draw the symbol, or you use the component wizard, the symbol wizard, to draw a symbol, or you can import it from a different library. And on the same time, you create a footprint and you add the PCB component to the PCB library. You draw or import a footprint, or use the IPC Wizard to create a footprint. You add the 3D model to it, and then you add it to the schematic symbol and you link them together. If you have a simulation model, you can add it to it. If not, you can move forward, compile it, and release it. So that's all for session number 8. Thank you all. I think we covered the creating components in Altium Designer, and we don't need to add any more information to it right now. So in our next session, we will talk about multi-layer PCB design. We will start by practicing 4-layer PCB and 6-layer PCB design and move forward with that. And after that, we will start the signal integrity, get into the signal integrity concepts and how we can design a PCB that can work at high frequencies. Thank you all, and talk to you in the next session.